So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm still the interim director of NITheCS in this setting up phase of the institution. This afternoon, it's a great pleasure to have Professor Steven Karataglidis as a speaker. Steven is a professor of physics at the University of Johannesburg, and at the same time, he's also an adjunct member of staff at the School of Physics of the University of Melbourne. And I guess at the moment he can't visit it for obvious reasons, yeah. But hopefully in the new year. Yeah. Before joining the University of Johannesburg, he was based at the University of at the Rhodes University, where he was also the head of department in physics. Prior to that, he was had postdoctoral positions at the Michigan State University, at Triumph in Canada, and at the Los Alamos National Laboratory in the US. Yeah. So his field of expertise is theoretical nuclear physics, and I apologize if someone is ringing at my door, but we will sort it out just now. But he's also interested in mathematical physics and the foundation of nuclear physics and quantum mechanics. Steven, we are very happy to have you with us today, and we are really looking forward to your talk. And before you start, sorry, I always forget to invite the participants to ask questions using the Q&A facility that you find at the bottom of your Zoom screen. And since we are not hundreds, you're also welcome to raise your hands, and we can give you the right to ask your questions in person. And after the talk, as we've done recently, Steven agreed to spend a few minutes with us in Kumo Space. So if you want to chat with him later, please join us in Kumo Space. I will post the link just now in the chat. Steven, please, it's your show. Thank you very much.
Thank you, Francesco, and thank you for the opportunity to give this talk. I just wanted to discuss today some recent work that I and my group and my collaborators have been doing, and it involves two problems, as the title suggests, of nuclear structure in the ST shell. And just to give you an idea of who is involved, in the MCAS work, and I will introduce that in the second half of the talk, my longtime collaborator, colleague and friend, Ken Amos from Melbourne University in Australia, Paul Fraser, one-time student that I co-supervised with Ken for his PhD, who is now at the University of New South Wales, Canberra campus in Australia, and Luciano Canton of the Padova section of the INFN in Italy. And the first half of the talk, which is on carbon-16, involves my current PhD student, Kulisa Murulane, and the work that I'll be describing was formed part of his master's work. So without further ado, now to introduce the subject, the heavy carbon and oxygen isotopes are of inherent interest, as both sets of isotopes contain neutrons in the SD shell. That is actually the 1s0d shell. There is a major difference, however, and that lies in there being an open 0p shell for carbon. The single particle spectrum I have from the shell model listed here, and that goes in a different type of spectroscopy starting with n=1. So there, while in the 1p shell, as given, the oxygen isotopes have a completely closed p shell, the carbon have only 4 protons in the p shell rather than a full 6. So, and we go one step further, but both sets of isotopes have neutrons in the SD shell. So what I will be describing is a combination of the two. So let's look at the mass 19 for a start. The isobaric chart here, we have 2 mirror nuclei, oxygen 19 and sodium 19, of which are of particular interest, as I said, and we'll look at in conjunction with the other 2 mirror nuclei, the pair fluorine 19 and neon 19. It's important to note that all mass 19 in this chart, mass 19 nuclei in this chart, decay by beta, with one exception, and that's sodium-19, which is unbound and decays by proton emission to neon-18. And that causes quite some problems in what I will be describing later. Let's start with the structure of carbon-16. We need to know a lot as we can. A lot of effort has been devoted to try and study the structure of carbon-16. And it is because we have the presence of two neutrons in the ST shell. Carbon-14 forms a closed neutron shell, neutron P shell. But as I said, the 0p proton shell is open. And we can also study the structure of carbon-17 as a neutron coupled to carbon-16. And it's a study we did quite some time ago with MCAS, as you will see later. And I apologize for that noise outside my building. Good Lord. So for the binding energies for the carbon isotopes, you see them listed there from 15 to 20 in MeV. And carbon-16 is quite bound. The separation energy is 4.25 MeV. Carbon-17 is loosely bound, as is carbon-19. Now, in the shell model that I'll be talking, I'll be using the nomenclature no core. Various groups use various different nomenclatures for this, but I will be saying that all 16 nucleons are active, and in the calculations that I'll be presenting from the shell model, it is through the 6 major shells, so that the space in h bar omega that I will be using is complete. But the simple model that has been used in the past in analyses of data to study carbon-16 has been two neutrons coupled to the carbon-14 ground state. What we do is a complete 4h bar omega model for carbon-14, a complete 2 plus 4h bar omega for carbon-16, using the same single particle basis and interaction, which in our case is the Zheng G matrix interaction from 95. The ground state wave functions in configuration space, I list them there. Carbon-14 is 63% 0h bar omega plus some 40% coming from 2h bar omega and 4h bar omega components. Carbon-16 is largely 73% 2h bar omega and the rest 4h bar omega. And the increase in the percentage of the 4h bar omega components, and remember these include configurations where the protons are allowed to move, indicates a far more complicated structure than the simple assumed models that have been used. So we're going to continue dealing with that. And the spectrum that we get for carbon-16, you can see there, experiment from the tunnel evaluations. And for the first 3 states, the ground, the 2 plus and the 0 plus state, we get incredible agreement. And we can see the cluster around 4 MeV, although there is a bit of a separation between the 2 plus and the 3 plus and 4 plus states. And the state at 6 MeV, which is anybody's guess as far as spin parity is concerned, 2 plus being one of the states, one of the spin parities postulated, we predict to be a 2 plus state. So here's the first test with regards to seeing whether we understand the structure within this model reasonably well and the spectrum passes. But we're also going to look at the elastic scattering data for protons of carbon-16, which is done in inverse kinematics with carbon-16 being scattered from a hydrogen target. And there is only one set of data, scattering data, from Japan, and we analyze these data using the Melbourne G folding model of the optical potential. That goes back to the review article that is listed there from Advances in Nuclear Physics 25. It uses an effective nucleon-nucleon interaction obtained from G matrices, so mean field and Pauli effects are included. Our starting interaction is the bond B. We create the effective interaction in momentum space, which we then map to coordinate space to be used in the DWBA programs of Jacques Reynal. And we use the one-body density matrix elements from credible models of structure, not just the shell model, but we have used mean field models in the past as well. The G matrix itself is a solution of the Bethe-Goldstone equation, and I list it there so you can see Q as the Pauli operator inside the integral, and the energies in the denominator there are mean field energies, so we never hit a pole because of the structure of those energies. The construction of the optical potential, once we have the G matrices obtained in infinite nuclear matter, we can see forms two terms, one direct, where the incoming projectile, the nucleon projectile, it can be a proton or a neutron, is the one that is scattered. But of course, because we are sending that nucleon into a system of like particles, we can also have an exchange term where that nucleon, incoming nucleon, knocks a like particle out. So the exchange term would have the incoming proton coming in, knocking out one of the bound protons in an elastic scattering event. The first term, the direct term, is known as the G-rho form of the optical potential. The non-locality, because we know from the work of Feshbach 60 years ago that the optical potential describing a nucleon-nucleus interaction is non-local by construction, by necessity, and it rises primarily and explicitly out of the exchange terms, and that is why there is a presence of the delta function there for the direct. The structure enters through the single particle wave functions in occupation numbers n, and for non-zero spin targets, terms with non-zero spin coupling may be included via the distorted wave approximation. We don't have that situation here. The structure of the target, as we showed in the review article and in work that we've done since this optical potential was constructed in the early 90s as part of my PhD, is critical. The one-body density matrix elements, simply an issue of that amplitude, reduced matrix element that is in front. The single particle wave functions can be either harmonic oscillator from a naive shell model, which in the case of exotic nuclei automatically gives skins, whether they be proton and neutron skins, or we could use Woods-Saxon wave functions with the appropriate binding energy set to the single nucleon separation energies, which gives then the appropriate extension of the density consistent with what is commonly called a halo. We try and avoid that particular nomenclature because in the case of lithium-11, for example, which is a halo nucleus, where we have two neutrons in the 1s shell, forming that neutron halo outside the lithium-9 core, that part of the wave function for lithium-11 only forms about 30% of the total wave function. The rest is a compact object, and beta decay study supports that particular structure. One thing that still is quite remarkable is that in this particular theory of the optical potential, there is no fitting. We predict the cross sections involved. And the example I like to use is the skin thickness calculation for lead-208 that we did back 20 years ago. And you can see 5 models of structure there for lead-208, 2 oscillator, 3 skirm, and you can see on the top half of the figure the proton density that we predict, and on the bottom figure that the neutron density. And in the case of the neutron density, where we have under 2 Fermi radius, the 2 models that somewhat overshooting or having too much neutron density at close quarters, those are the oscillator models. The rest are all the skirm mean field models. And here we have a comparison of electron scattering form factor, the elastic electron scattering form factor, the longitudinal form factor, compared to a data analysis. And we can see quite good, reasonable reproduction up to 3 inverse Fermi in momentum transfer. And the best model that seems to work here is one of the skirm models. This is just for illustrative purposes. For nucleon scattering, I can look at 40 MeV proton and neutron scattering, protons in A, neutrons in B, and we can see again up to 80-degree scattering that we get reasonable agreements with the data as predicted, but the best seems to be the same skirm model as done with the electron scattering. Same thing we observe at 65 MeV scattering. again, protons in A, neutrons in B, and at 200 MeV. Now we're getting to much larger momentum transfers up to 60 degrees in the scattering angle in 200 MeV, and we start to see some disagreements as the cross sections become very small. So having said that, we now come to look at the scattering of 300 MeV protons from carbon-16. Those are the data that exist as were obtained from RIKEN. No, sorry, Osaka, I think RCNP there. And the line is the prediction that we make from the shell model densities and the Melbourne G-folding optical potential. And it is a prediction. There is no fitting involved here. So we can now have a lot more confidence in using the shell model wave functions in what I'm about to describe. And that is the electric BE2 transition value for the E2 transition from the 2+ state to the ground state in carbon-16. And the reason why this is of interest, these are the existing data from Japan, from I think the Vida King at the time was at Berkeley, another one from Japan, and Fortune did an average of all the existing data. And you can see that they almost span an order of magnitude. It's a very difficult experiment to do, given that this transition, as measured, is basically at zero momentum transfer. So how do we make sense of this? Well, the shell model results, bare operators we get with no effective charge, and an effective charge with regards to electric or magnetic transitions. We just ascribe an additional partial electron charge to either the protons or the neutrons or both. We get 1.35 E squared Fermi to the fourth, same units. For 0.08 electron charge, we get 2.61, 0.12 electron charge, 3.39, and the adopted value that we use from Ong, and there are reasons in the paper that we published last year, is 2.6, and we get quite good values. Now, the papers involved, when they were using just a simple two neutrons outside of carbon-14 or coupling to carbon-14, required an effective charge of 0.5 E to predict to get the BE2 value, and that is necessary in that regard, because we're describing an electric transition which requires the motion of charged particles, and neutrons, of course, are not. So they had to give some effective charge. In this case, the effective charge here is an acknowledgement still that the wave functions are not exact. They are model wave functions and still may have some limitations in terms of truncation of the model space, in terms of single particle basis, or in terms of the expansion in H bar omega. So let me go now to mass 19 nuclei. I've given where the closed shell is at the P shell, that's oxygen 16. And we're going in there into the SD shell for positive parity states only. But we are also considering in this model, we want to look at the negative parity states as well, which requires some transitions of particles of the neutrons between the SD shell and the FP shell. And that's at 1 H bar omega in energy between the two major shells. So modeling mass 19 using MCAS, or as I otherwise call it, a shameless plug of the book we published 2 years ago, which describes in full the development and the complete theory of the multi-channel algebraic scattering theory, which is a low energy scattering theory to allow us to use and obtain information not only about cross sections, as one would expect with scattering theory, but given that at low energies, when a nucleon comes into the nucleus, it can form resonances in the compound nucleus A+1. So we're using MCAS to describe mass 19 nuclei as the coupling of a nucleon to a mass 18 core. And I present the isobaric chart again, and we have the two sets of mirror nuclei, oxygen 19, sodium 19, and fluorine 19, neon 19. The cores that we start with is we need to understand oxygen 18 and neon 18. And this is a situation that I talked about or referred to earlier, and that's the understanding of carbon-17 in terms of the coupling of a nucleon or a neutron to carbon-16. And we're comparing that to the situation where we are describing the states in oxygen-19 with regards to oxygen-18 plus a neutron. And the two situations are not similar. And the reason for that is for the fact that we have, even though we have in both carbon-17 and nitrogen and oxygen-19, 3 neutrons in the SD shell, the open 0p shell in carbon-16 makes all the difference, as you can see there. So let me look now at the information that we need. We're doing a couple channels formalism. Oxygen-18 and neon-18, these are the structures of the target states. And we are assuming that they are indicative. We can see sort of the separation of clusters of states consistent with a vibrational nuclei. So we're using the vibrational model to define our interactions between the target states and the incoming projectile. And here we have a comparison now with carbon-17 and oxygen-19, states identified by 2J. And you can see that we're doing quite well in both in carbon-17, not so well in oxygen-19, even though we get the spin parity of the low energy states. In oxygen-19, we don't exactly have the right separation between those 3 states. And the similar thing occurs in carbon-17 as well. They are very large calculations in terms of the diagonalization of the matrices involved. But we can see then we have 1 plus 3 plus 5. Sorry, half plus 3 halves plus 5 halves plus. Now we look at oxygen-19 as a neutron coupled to states in oxygen-18. Now, the major advance in MCAS compared to other coupled channels models is that we do the channel coupling and the solution of the Lippmann-Schwinger equations, the coupled Lippmann-Schwinger equations in momentum space. And that allows us to not only describe the open channels as one would have above the neutron plus oxygen-18 threshold, the states listed above 0 there, which is where we put the threshold. But we can also assume that all the channels are kinematically closed and we can get the bound states, those below the threshold. And you can see there that we do exceptionally well for the spectrum of oxygen-19 as compared to MCAS as compared to experiment. There is a little bit of fitting involved with regards to the interactions that we use, but that's only in the bound states. And anything above the scattering states are predictions. And we can see quite good reproduction of everything. I'm not sure how many of the bound states, I can't remember offhand, it might have been a subset of those bound states that we use to form the interaction potentials. Now, if we switch from neutrons to protons and we use the same interactions as we just used in the case of oxygen-19, and including the Coulomb interaction, because now we have a proton on neon-18, we can get the spectrum of sodium-19. And you can see the comparisons between one and the other. And I think the full MCAS calculation is B. I cannot remember what A is off the top of my head. And there we have neon-19 in comparison to MCAS. In this case, neon-19 as neutrons on neon-18. And fluorine-19 as protons off oxygen-18. And there we have again fluorine-19 and neon-18, but now as couplings of different clusters. In one case, protons of oxygen-18 for fluorine-19, you can see it there, or the triton of oxygen-16 or alphas of nitrogen-15. and we can do the same thing, the mirror side on neon 19, and we get similar, if not identical, results as the energy goes up. Now we look at the cross-section with regards to the scattering of neutrons from oxygen 18. Now we run into a problem. We can see roughly the structure and the magnitudes of the cross-section reproduced reasonably well, but the positions of the resonances in oxygen 19 do not correspond 100% with what is observed. There are some movements in the predicted energies of the resonances, but we get roughly the order as observed in the data. And the reason for that is lack of information, especially in the case if we are relying on the mirror system to find states in sodium 19 with information from neon 18. We do require information on the structures of the core in these calculations. And when we are using exotic nuclei or trying to construct a suitable spectrum for exotic nucleus, we find very little data available. They are very difficult experiments, and the more exotic, the less information there is in the literature because of the difficulties of the experiments involved. So you can see we can get roughly the resonances, the one at just above half an MeV, for example, in neutron energy. But we can also see this wide state between 1 and 2, wide resonance between 1 and 2 MeV. But as a collection of the number of states, we can see roughly position, although offset, the resonance at 2.5 MeV and so forth. If we look at alpha scattering from oxygen 15, there is an alpha version of MCAS involved. It requires different angular momentum couplings to a nucleon coming in for the fact that the alpha is spin 0 rather than having a spin 1/2 particle coming in. We can see again the background cross sections are reasonably well reproduced, but now we're not seeing the resonance structure as we had before. And again, that's because there is not as much information on oxygen 15 as possible. And you can see in the diagram on the right, the spectrum of neon 19 as alpha plus oxygen 15, there are many states that we need to look at as far as that's concerned. And we're doing okay grossly with regards to the low energy spectrum. And then as we go up higher in energy, going into the high level density part of the spectrum, but we don't see exactly or match exactly that particular structure as observed. So to conclude, which is a lot faster talk than expected because this is online, of course, but there'll be plenty of opportunities for discussion. In the case of carbon-16, a large-scale shell model does a better job of explaining the limited available data. That's the spectrum, the available cross-section at 300 MeV, and the disparate values for the BE2. But simple 2-neutron model cannot adequately explain electromagnetic data. In this case, it's an electric transition requires the involvement of charged particles. That's necessary. In the case of mass 19, as I've just described, the limitations of MCAS are largely due to lack of spectral information regarding the core nuclei and the collective model descriptions of the coupling. And it is particularly problematic in the case of exotic unbound nuclei where there is no such information. There is one more aspect, which is not so much in this case, but we are starting to see it all in exotic P-shell nuclei as well, is when the spectra of the nuclei do not exhibit easily identifiable collective model features. And then it becomes a major headache, for which in future we hope to get to, has been the plan for quite some time, lacking of manpower, to do something based on the shell model as opposed to the collective model. So on that, thank you. I'll leave it open now for questions.
Yeah, thank you very much, Steven, for this very interesting insight in new developments in theoretical nuclear physics. That was quite interesting. Thank you so much. I don't see at the moment any questions in the Q&A or in the chat. but as I said before, I would like to invite the participants to raise their hand, and we can give them immediately the right to ask the question in person. Yeah.
Of course, and I've got a lot more time now, given that the talk finished early.
Yeah.
Previous occasions where I've given this talk, it's been far more interactive.
Yeah, no, that's, unfortunately, we need to make use of these virtual tools at the moment. We don't have many other options, I fear.
No.
I think our participants are a bit shy today.
Indeed, I can't see anything.
Yeah, but Steven, maybe you can tell me, if I understood it correctly, you started this work together with your colleagues in Australia. Yeah, are you the only group in South Africa that looks at these kind of issues?
Yes, we are. Nuclear theory is a lot smaller community now in South Africa than it was maybe 30, 40 years ago, of course. And to do low energy nuclear physics, it's very much underrepresented, unfortunately, at the moment. And most of the nuclear physics is being done with involving relativistic heavy ions within the SA-CERN program.
Yes.
We have a hand raised.
Yeah, here we go. I already gave to Kile the right to speak. Please, you're welcome to unmute yourself and ask your question, please. Maybe I can ask to unmute. To Kile, just press the unmute button and then you're ready to go. No. I'm not sure. I'm not sure, Steven, what is not working.
Neither am I.
Maybe there's an issue. Tukile, if you have a problem with your microphone, you are welcome to use the chat to ask your question. You have all the rights to speak at the moment. I can't unmute him from here. Okay, I'm not sure. Yeah. And there is. Okay, now there's a second attempt. I allow, yeah, maybe it works now. Yes.
Yes, apologies.
No problem.
My computer just started updating when I was speaking. Okay, so thank you so much for the presentation. And you just mentioned something about nuclear reaction theory, about being underrepresented in South Africa. So I'm gonna now start from there and ask what can one do to join the team or to sort of like take that path of theory, and then
first things first, we can have a chat. That's where it starts.
Okay.
It would involve facilities where you are. These calculations. These are more numerical. My numerical side of my research, computer intensive. The calculations of MCAS involves a supercomputer at Melbourne University, and that's where the bulk of the calculations are done. The shell model calculations, the matrices are typically anywhere between dimension 10,000 to 50,000, which we can do these days on a desktop, but it has to be a powerful desktop. So that's the part effort. But on the physics side, can I just ask quickly, where are you based?
I'm affiliated with VETS and Itemba Labs. So I'm based at Itemba Labs.
Up here or in Cape Town?
In Cape Town.
Okay, you're an experimenter then?
Yes.
I'm assuming.
Yes.
Okay. It requires a strong background in nuclear structure and reaction theory, as well as a strong background in quantum mechanics. So it's because even though a lot of it involves running programs, a lot of it is developing programs, as MCAS was developed from scratch by our group. And you need to understand all of that to make sense of the results coming out of the programs. So at the moment, I have always had an ad within NITEP and NITheCS for asking for students. And they've been few and far between, unfortunately, but I have one very good one, and he's working on mathematical physics at the moment, but his master's was in this type of work as well, as you saw. So by all means, we can talk, we can chat, and see how you might want to become involved if you wish.
Okay, thank you so much. So now I have a question on, so on your conclusion, number 2, the last sentence says, this is problematic in the case of exotic unbound nuclei where there is no information. So is this experimental information that you are referring to? And if it is it we don't have information because of experimental limitations, or is there something else?
It is a form of experimental limitation in as much as you can't form a beam of unbound nuclei. That's just impossible. So if we're dealing with a core situation which is of an unbound nucleus, we have to rely on predictions from the shell model, and there it is basically guesswork, because we have no spectral information to form. Those states, those resonances can be formed in other experiments, for example, in transfer experiments between heavy ions, leaving a daughter nucleus as an unbound nucleus. So that spectral information can be found, but as you saw in the plots that I showed, determination of spin parity is incredibly difficult, and we need that spin parity information as well. So, these are fiendishingly difficult experiments, and I speak as one who used to be an experimenter long ago. So,
all right.
So I can still carry on a conversation in that regard, and I have close collaborations with the experimental groups at Saclay and Ganil in France, for example, as well as the experimental groups at Riken and Tohoku University in Japan. So, it is a very difficult information. That's why you find very, very little information in the case of unbound nuclei in terms of the spectral information of sodium-19, for example. There's only basically ground and first excited resonance. That's it. And we need a lot more information in order to make use of trying to see whether our predictions work or not.
All right, thank you so much.
Thank you to Kila, thank you very much. And now there is another question by Emil. Please, Emil, just unmute yourself and you're welcome to ask your question.
Okay, thank you, Professor, and thank you to the speaker for this talk. I see that he's treated the nuclei as a two-body problem, and he's calculating some important values like probabilities of electric dipole transitions. So I just wish to find out, like, for example, the nucleus Fluorine 19, for example, is it possible to treat it as a three-body problem? And is the binding energy, is it known accurately?
Fluorine 19 is there is quite a lot of information available, no question there. And I have to correct you, these are not two-body models. When you're doing a coupled channel calculation, as we have here, we're dealing with a collective model of the core nucleus, and in the coupled channels formulation of low energy scattering, the channel coupling gives rise to many body effects. And that's why those calculations are difficult, because that's how many body effects are included. In the case of the BE2 as I described for carbon-16, all 16 nucleons are involved in the calculations of the wave functions of carbon-16. Again, many-body. So these are not two-body problems, even though we are saying as a coupled channel model, we have a nucleon coming into a core nucleus. But because we are treating the core as a collection of 6 or 7 states from the ground up and allowing for the nucleon to couple to any one of those states, and then we have intermediate couplings as a result, and in the formulation of the compound resonances in the A+1, then it becomes a many-body formulation. And so and that involves a large diagonalization of a large matrix as well, because of the fact that the channel couplings become very large. The number of channel couplings become very large. That's the one aspect that I didn't describe in terms of this model to go into any great detail, because it's all described in the book for one. And there, it requires, if one goes to any one of our papers to see that formulation of channel coupling, may require a course for me to give at some point online. And I have been in a position to do that in other aspects of my research as well. So they are many body calculations in the true sense of the word.
Oh, okay, thank you very much for that clarification. So if I may try to pose my question this way, for example, carbon-16.
Yes.
Can I do a three-body calculation on it and treat it as, for example, carbon-14 and 2 neutrons? I don't know, I'm not sure if carbon-14 is particle stable, but suppose it was particle stable, Adam. Is it possible to
carbon-14 is particle stable. It's a bound nucleus, and it beta decays much more slowly than predictions would have you give. That's the one responsible for carbon radio dating.
Yeah. Oh, sorry. Yes. Yeah, that's true.
If you remember.
That's true. Yeah.
So that can be done, but again, the issue is not the fact that you've got the 3-body situation, the carbon-14 and the 2 neutrons, is how do you get from that coupling an electric transition? You need to involve the protons.
Okay.
That's the point I'm trying to make here. And I can get an electric transition just purely from the protons in the P shell if we assume that the carbon-16 ground state might have, for example, all four protons in the P shell in the P3 halves orbit. All I need to do is break one of the pairs, put one of the protons into the P1/2 orbit, couple the two together, and I can go from a 0+ state automatically to a 2+ state without involving the neutrons at all. That is why one needs to involve the protons explicitly in this situation.
Thank you very much, Professor.
Thank you, Emil, for your question. Steven, I don't see any further questions at the moment. Then I would suggest that maybe we start a procedure of thanking you for your nice talk and for the time spent with us this afternoon. And I would then again encourage the participants maybe to try to join us in Kumo space for a more informal opportunity to chat with Steven. And sometimes we made the experience that a less formal setup is more inducive of chatting and asking questions. So if you go to the chat, you see the link. You just please click on the link. If you haven't used it before, you just have to quickly register. But that will take you 10 seconds, and then we can interact another 10 minutes or so with Steven, who indicated that he has a 10-15 minutes time after the talk. Yeah,
I can go a little longer, given that we finished early, Francesco. That's
yeah. No, let's see how it goes, how many people join us. Yeah. So thank you very much again. I hope you will have by latest tomorrow morning the invitation for the next colloquium. That will be probably the last one in for this year. Yeah. And I'm looking forward to see all of you or some of you in Kumo space just now. So Steven, thank you very much for your time. We really appreciate your effort to share your nuclear wisdom with us. Yeah. So thank you very much.
Thank you, and I'll
Thank
join
you.
you in a second.
Have a good afternoon, everyone, a good evening, and please stay safe. Don't do silly things in times of Omicron. Yeah. All the
Yes.
best.